Hello, everyone. Welcome to the 19th episode of the ZEISS Micro Minute. My name is Amita Gurur, and I'm coming to you live from the ZEISS Microscopy Customer Center in Dublin, California. Every Thursday at 1 p.m., one of us imaging scientists comes to you live from our microscopy center, and we hope that you all join us for a very engaging session on one of our microscopes. So today, the topic that we are going to look at is quick screening and targeted high-resolution cryo LSM imaging. So let me go full screen and share. Yep. So the LSM 900 is part of our cryo correlative workflow. And what is a correlative workflow in the cryo realm? So cryo microscopy essentially is imaging grids or samples on a grid that have been vitrified and in the near native state. So you can image the same sample and the same grid between two instruments. What you see up on the screen is our LSM 900. The light microscope, and the exact same region can be imaged on our cross beam or the focused ion beam scanning electron microscope. So this is part of the correlative workflow set of instruments. But what I have seen recently is also some of our collaborators and users have utilized the LSM data along with other EM instruments as well. So I have been doing some cryo imaging for the past couple of years, and hopefully in today's session, I'll be able to share some of my learnings from imaging a multitude of samples from mammalian cells, yeast, so on and so forth. So let's dig right in. What is the cryocorrelative workflow? In a nutshell, you're looking at imaging grids on the light microscope at low mag objective using the 5x and then the 10x. And you do this using a multitude of contrast methods, for example, transmission, reflection, and then you utilize the high NA 100x objective to do confocal imaging. Once you do that, you can take the grid over to the crossbeam, and you can do this very seamlessly utilizing our correlative project, which is called the Zen Connect, which keeps all of the files in context, and you can image the very same regions on the crossbeam, create a lamella, or perhaps do 3D volume imaging. So that's in a nutshell what the correlative workflow is. But in today's session, specifically, we will be focusing only on the cryo LSM imaging. So the components that are part of the cryofluorescence imaging setup are the Lincoln cryo stage. So the Lincoln stage is a stage that comes from Lincoln, and this is cooled down with liquid nitrogen. So what you see up on the screen here, you have a dewar where you pour in liquid nitrogen, and you have a loading area where you load your grids into a cassette. Now you have a multitude of cassettes that you can use either for naked grids or auto grids or high pressure frozen planchets, for example. And you also have a display that will display the temperature of the chamber, the bridge, and the dewar. And on the right, what you see is the Axio imager stand with the Lincoln stage that has been loaded onto the stand. And so this is our setup for imaging on the light microscopy side. So what kind of samples do we image, right? So essentially, like I mentioned at the very beginning, these are vitrified samples, and you want to maintain vitrified nature of the sample. So you don't want anything that will cause devitrification, essentially. So what kind of samples? So these are cells, for example, mammalian cells that are grown on an electron microscopy grid. And these grids can have a support film, for example, a carbon foil or a foam-wire coating. And these grids are plunge frozen. And once they are plunge frozen, they are stored at minus 196 degrees Celsius. And all of the imaging is done at minus 196. So in a nutshell, this is essentially the type of grids that we are imaging on the LM. Now, what the advantage that you have on the LSM 900 is it also comes with the ARIES scan detector. So not only do you have confocal imaging, but you also have the additional advantage of getting really high signal-to-noise ratio and also better resolution, almost 1.7x times better than the confocal. So what you see here is an example from dictyostelium discoidum, a cryoconfocal compared in side by side with the cryo ARIES scan, just giving you much better resolution. So all of this is done on the LSM 900. And what you see here on the screen is that exact instrument. Now, when I start imaging on the LSM 900, what am I looking for? So there are certain criteria that I have in mind when I'm screening these grids. So what does screening grids even mean? So when you prepare your grids, either via high pressure freezing or plunge freezing, for example, you prepare a bunch of grids in multiple grid boxes. Now, if you were to take this grid straight to the EM, your field of view is less, but you're also not able to assess the quality of the entire grid in one shot. It probably might take you a little longer. So when I'm on the light microscope with the 5x objective, I'm getting a full shot of the grid, the entire grid in one in one shot. So essentially what I'm trying to assess for the grids is structural integrity. What do I mean by this? So when we are handling with the tweezer, is there any bending in the grid, right? So we don't want grids that are broken. The film has to be intact, so you don't want holes in your grid, right? So with the 5x objective, I'm able to assess the structural integrity and the film integrity in one shot. I'll give you some examples. I'll show you some as we progress through the talk. I'm also looking for confluency. And this is very critical because if it is very confluent, then correlative workflow becomes a little challenging. So you really want to have cells that are just right. For example, a couple of 3 to 4 cells within a grid square. So you don't want cells on the grid bar. You want them right in the middle of the grid square, also right in the middle of the grid. Having these cells at the very edge of the grid doesn't allow easy cross-beam workflow. So you really want them right in the middle of the grid. And also ice contamination. We don't want ice contamination, as you might appreciate. So I'm looking for these criteria. So let's look at an example of why ice contamination is essential to evaluate. So if it's samples that are perfectly frozen, it's in a very thin layer of ice. So using reflected light on the light microscope, you are able to judge the thickness of ice. So in this video that's playing on the screen, the top panel shows really thick ice layer, which is around 20 microns thick, and cells are embedded within this ice layer. But imagine trying to dig through this ice on the crossbeam, which might be quite challenging. So ideally, we really want very thin layer of ice, and this is easily accessible on the light microscope. So what you see on the screen is an example of a good grid, as I call it. What does that mean? So on the light microscope with the 5x objective, I'm able to assess the quality of the grid within 3 minutes. And this is essentially quite an efficient workflow because I'm not spending too much time on the electron microscope. With the light microscope, I'm able to get a full shot of the entire grid with the 5x objective. So in this example, there are no tears in the film, and there are no tears in the grid itself. So there's what you see is good structural integrity of the grid. This is the center of the grid, and we try to image cells right in the center of the grid. And the confluency looks good. So this is an example of mammalian cells with the nucleus labeled with fluorescently labeled H2B, histone protein. So very clean confluency. So moving forward with that same grid, here's the example of a small grid square where the cells seem to be frozen really well. You see all of these ripples. This is looking at an image with using reflection on the LSM 900 combined with fluorescence. So you get the overlay of fluorescence and reflection in this one image. And then this is an ARIES scan image, a Z stack. So this is just a volume projection of a Z stack that was collected with the 100x objective. The next image or the video playing is showing you a ZenConnect video. Essentially, what is ZenConnect? It is a project or a collection of files that keeps all of the information in one place. So you see an overview image, which is coming from your 5x, and then it gets overlaid with the 10x image, and then all of the detailed images coming from the 100x. So in one shot or export of the video, I'm able to analyze where is all of the information coming from different parts of the grid. So this is just an example of a ZenConnect video. How do we go about the LM imaging session? So what you see here is my colleague cooling down the stage. So the linkum stage first needs to be cooled down. So you pour liquid nitrogen into the dewar and you cool down the stage, and you can monitor the temperature on the display panel of the linkum stage. And on the right, the image shown is you then load your grids into the holder, and you have a choice of different holders. What I have here is the linkum holder that will allow you to image within the light microscope. But if you were to image the same grid between the two instruments, you also have correlative holders that you can utilize. So you load the grids onto the cassette, and then what you see up on the screen is a Zen software interface. So I have launched our Zen software, and the first thing that you want to do is you expand this tab that says cryo temperature. So you're able to constantly monitor the temperature of liquid nitrogen. And this allows you or gives you the peace of mind that your samples are not being devitrified, during the process. And then what you do next is you create a ZenConnect project. So that's the first thing you would do when you start an imaging session. So essentially you assign a folder where you want all of the images to be saved, and then you give a project name. And once you do that, you just say OK, and then you have this essentially an open canvas where you start building all of the images. Then you click on the acquisition tab on Zen, and under that tab, you have all your pre-built experiments. For example, you can have an experiment for the 5x overview, which has the channels populated for reflection and transmission typically, and then a 10x experiment, which will give you an idea of the fluorescence signal coming from the sample, how good is the signal, how confluent are my cells, so on and so forth. So that's the first step when you start imaging on the light microscope. And in the next slide, let's look at some examples of some Connect projects. So in this example, I have a Connect project from mammalian cells. So let's go ahead and open the project file and look at how things look when they are arranged in a Zen Connect project. So as a first step, I just go to File, open a project file, and then what you see up on the screen coming up is an imaging session where all of the information is very well organized on the right side of the panel. So under the Zen Connect project, Zen Connect tab, you see all of the sessions. So there are 3 individual sessions that I typically utilize while I'm imaging. So you have the 5x, an imaging session for the 5x objective, an imaging session for the 10x objective, and then another imaging session for the 100x objective. And all of this data is very well organized by the date and the time. So it's almost like your notebook that you can refer to after the fact. Like months later, you have the idea of exactly where you imaged the sample, and gives you contextual information as well. So you can zoom in and zoom out of the project file. And what I just opened was the 10x image, and this gives you a good idea of the confluency. But you also notice that there are some cells that are beautifully spread out, and those are the type of cells that you want to be imaging. But there are also some cells that I point with the cursor on the screen that are rounded. So the 10x image gives you an idea of what kind of cells I want to be imaging. For example, if there are rounded cells, perhaps these cells have not been allowed to grow longer. And so that's why you have these rounded cells, and you don't want to be imaging those. You want to image cells that are beautifully spread and have the regions of interest that you're looking for. And as you zoom in, I'm highlighting one of the 100x images. And if you double click, if you highlight that file on the Zen Connect project, you can double click that image, and what you see up on the screen is a ARIES scan image obtained with the 100x objective. So that's mitochondria in red and nuclei in blue. So that's just a far red mitotracker image. So essentially that's giving you an idea of how you can image a grid with 3 different objectives, but as you image, they're all perfectly organized within a Connect project file. And you can zoom in and zoom out, and you get the contextual information of exactly where you imaged these cells. And typically, we image 3 different ROIs. So you can utilize these ROIs for subsequent imaging on the electron microscope. I also open another project file here just to give you an example of mammalian cells on a grid. But in this example, I also have cells that have been labeled fluorescently with a mitotracker, but also with a nuclear pore complex in GFP. So it's a dual channel fluorescently labeled cells. So we're waiting for the Connect project to open. And similar to the previous file, you also have similar imaging sessions on the right panel. But as I zoom in, so this is an auto grid. And as I zoom in, the overview image was acquired with the 5x, which you see here. There's a little bit of ice contamination that's obvious with the black particles on the grid. Going back to the Connect project, as I zoom in, you see a 10x image that I just opened. So here I have combined reflection, transmission, and fluorescence. So this gives you a good idea of the confluency of the cells. What you see in magenta is the mitotracker, and what you see in the ochre color is the reflection image of the grid. So zooming in to one of these cells, so like I mentioned, we typically image 3 ROI. So as you zoom in, you can highlight that image. It highlights that exact same image on the Zen Connect project the tree view. And here is an AD scan image of that cluster of 2 cells. And splitting this panel, what you see on the left is your mito tracker in far red and the nuclear pore complex in green. So this is just giving you an idea of how a typical light microscopy imaging session progresses. Of course, on the right, on the 5X image, you also see, because of the handling of the tweezer, there's a little hole in the grid. But if the center is good, we pretty much go ahead imaging that. I think I also have another example just to show you how we go about disqualifying a grid. In this example, there's a lot of ice on the grid. And just to give you an example of how we might just disqualify using the 5X and the 10X objective. So this is looking at the overview of a ZenConnect project, 5X image. And what you see, the spider webby look in the transmitted light is thick ice. So imaging this with the 5X gives you an idea of perhaps we don't want to go further for electron microscopy with this grid. And the 10X image overlaid on the 5X shows you that very thick ice. And this is the split view of the fluorescence, reflection, and transmission image, all from that single 10X image captured together. So this is just to show you a couple of different examples from the light microscopy imaging session and how we might either qualify or disqualify grids for further electron microscopy. This final example was an example of a disqualified grid where I would not go ahead with electron microscopy because there is very thick ice. All right. Another example from yeast cells. So what you see on the left is a 5X overview of combining transmitted light and reflection. You can see the grid bar in the transmitted light. However, what you see here is a very thick crust of cells. While this might be great for volume imaging, this is extremely challenging for correlative imaging. So again, just an example to show how screening of grids on the light microscope saves you a lot of time and perhaps headache on the electron microscope, because this is not a grid that I might use for correlative imaging. What is ideal is, this is an example from yeast grid where you have a 5X overview, but you have yeast sample very sparse or scattered throughout the grid, and you only have a couple of clusters within a grid box. And this is ideal for correlative imaging. In this example, you just have 100X AD scan image of these yeast cells that have been imaged through that grid box that you see, and then overlaid on the EM image, the exact same region. This is the ideal density. Examples of disqualified grids. This, as like I mentioned, within 3 minutes of the imaging session, you can disqualify. For example, here, right around the center of the grid, there are many empty squares, which essentially means there are holes in the film and not many areas to image. So I would disqualify this grid. Again, thick ice on this grid, so another example of a disqualified grid. Big tear in the grid, thick ice on this one. So just giving you a few more examples of how I might disqualify these grids on the LM microscope right away. And then finally, once you have your ZenConnect project from the light microscopy, this video just shows you how easy it is to use or utilize the light microscopy data to navigate that sample for sample navigation on the crossbeam or the electron microscope. So if you just double click on the Connect project, what you see on the screen is you can navigate your stage on the cross beam to go to the exact same region. So you could be imaging the exact same or the same cluster of cells that you imaged on the light microscope. It's as seamless and as easy as it looks on the screen. So you just double click on that Connect project that came from your light microscope, and the stage automatically moves to that exact same cluster as you see playing on the screen. So that's an example of showing you how easy correlation is of the exact same cluster of cells. With that slide, I can leave you with an example from protoplasts that we imaged on these grids. So essentially what you see up on the left is a Zen Connect overview of the 5x, 10x, and 100x images. And this is the region from where these protoplasts were imaged. And this is a Z-stack. What is seen in yellow is cellulase synthase, and the chloroplasts are in red. So this is a Z-stack, individual slices through the Z-stack using the ARI scan. And then finally, another ROI that was imaged from the exact same grid, taken over to the electron microscope. This last video that I have from this presentation shows you how you can zoom into the light microscopy data, overlay a slice from your 3D volume image, and then you can correlate the exact same region from the light microscope using data from the electron microscope. So this is essentially what we do in the cryo correlative workflow, where you take images from the light microscope, image the exact same grid, same ROI on the electron microscope, and you can overlay that information from the EM onto the LM data. So with that, I have come to the end of my presentation. And then I want to leave you with this information, which is essentially we hold a lot of workshops at Dublin, where we are located. So we call these the Skill Builder workshops. So please feel free to scan the QR code and register for these workshops, because we hold in-person and virtual workshops for all of the imaging technologies that we house here at the Microscopy Center. So please feel free to check out the upcoming workshops. And if you're interested in learning more about our instruments and getting trained on them, here is a free resource of training videos. So please feel free to log on to our ZEISS portal, where you have access to all of our training videos. And if you want to check what are the upcoming live streams, where one of my colleagues will be here live at ZMCC, that's your QR code to check what our upcoming live streams are. With that, if you have any questions, please feel free to put them on the chat, and I'll be happy to take questions from you. Thank you. See you next time. Thanks for joining.